Guys, this is take 2 on our logarithms and exponentials part 1 video. My apologies for the first one being really low res, so this one's going to be a little bit better. So let's start off by going over the basic properties of logarithms and exponentials. We're going to take a look at the graphs, and we're going to take a look at how to evaluate these functions, as well as looking at some of the more simple logarithmic and exponential expressions. So to get us started, let's take another look at the graphs. You might remember in graphing with transformations, I did mention the logarithmic and exponential functions. So we have practiced graphing these with transformations, and we have seen them before if you are some of my students. But if you're from another class, that might not be the case. So let's take a look at graphing probably the most infamous exponential you're ever going to see. So the most infamous exponential would be y equals e to the x. And what you'll see in calculus is that this is probably the most common exponential you're ever going to see, because it's the exponential that has very unique properties, such as the fact that the derivative is itself, and there's a rich history to how it was discovered that I'll let you guys learn in calculus. But for now, we just need to realize that it's going to be the most important exponential, and we should get a little comfortable with what this e thing is. So e is approximately 2.7182 ... Now the ... does not mean that it repeats. E is a non-terminating, non-repeating decimal. It's not rational, and it's a special kind of number called a transcendental that you guys will again learn a little bit about what that word means in calculus. So for our intents and purposes, we won't be writing that e is 2.72. We will just be leaving e as is. So let's take a look at the t-chart and see how we'll write it. Now, you might remember from when we talked about domain that the domain of an exponential function is all reals, which means I can choose any x's I want to plug in. So I'm going to choose -2 through 2 as a good starting point, and then I plug that in to get my points that I'm going to graph. And we'll simplify these here in a second. So a negative power means that you take the positive version and put it in the denominator of a fraction. So 1 over e squared and 1 over e, and any number to the power of 0 is 1. And e to the power of 1 would just be itself, and then e squared, no way to simplify that. So now that we have the exact coordinates, when we actually want to just sketch a quick drawing of this, we're not going to be able to exactly, plot the perfect 1 over e squared, but we'll label the point that way. And for our own visual approximation, we'll just write down that e squared is about 7.39, and then 1 over e squared is about 0.14, and 1 over e is about 0.37, and then we already have that e is about 2.72. Okay, so we're using the tilde. We're very loosely approximating this, and this is just for the sake of us getting a somewhat to-scale graph. So moving to our xy axis, -2 at 0.14 would be very, very close, pretty much touching. At -1, we'd be at 1/3, so slightly higher, but still pretty close. At 0, we'd be at 1. At 1, we'd be at 2, and about 3/4, just a little bit less than 2 3/4. And then at 2, we'd be at 7, just shy of 7.5. So that's 8, and it'll be about here. Sorry. Okay. Now we're going to connect those. And let's think about how to extrapolate this function. So how is this function going to behave with its end behavior? So if we think about plugging in very, very large values of x, when you raise e, which is about, you can think of it kind of as like 3. If you raise 3 to a really large power, you're going to get a really big number. So this must be headed to positive infinity. Okay, but to the left, it's not going to be the case that it's headed to negative infinity. So if you think about what happens as we plug in these negatives, like -2 and -1, it looks like we're getting really, really close to 0. Okay, so why would that be is because when you have a fraction that's 1 over a number that's getting really, really big on the bottom, but you're still having a 1 on top, you're just getting a very, very, very small fraction always. So it's never getting negative. It's never going to negative infinity because the sign of the number is still positive. It's just that the bottom is getting big. So you're getting a fraction that's ends up being a decimal really close to 0. So let's draw in a red dotted line. This is called an asymptote. Okay, and again, you guys have seen this when we graphed with transformations. So our asymptote for these exponentials are always going to be at y equals 0 for the parents. And then as transformations are applied, you guys might remember that the asymptotes can shift. So we'll just say that the asymptotes move with the graph. Okay, so now's a great time. If you're coming to this video fresh, you never watched my graphing with transformations video, you might want to give that another look and just take a look at how graphing with transformations would apply to a function like this. Okay, so that is our exponential, our favorite one, my favorite one. It's going to be your guys' favorite one too. I trust you. Okay, so let's take a look at the other kind of graph, a logarithm. So we're going to look at, again, we're going to look at the most famous one. The most famous one would be ln of x. And that is a fancy shorthand way of writing log base e of x. So basically, why did this happen is because back in the day when logarithms were being developed, we're talking 1600s, 1700s, when these were being developed, there wasn't a lot of typewritten material for mathematics. And for people to produce typewritten material in mathematics, it was pretty challenging. So basically, people said, you know, it's much easier to scribe this and get this down if we just drop the base. So it became a convention to, instead of calling it like log base e of x, to write it as ln x, but it's still morally the same thing. So when we deal with a logarithm asks the question, what power? So you'll plug in a value in for your x, and it'll be asking the question, what power? So when we're dealing with something that's kind of special, like base e, when we plug in x values, we don't really want to plug in our usual suspects. So let's look at the biggest, I'm going to write the biggest mistake that I'll see people do, and then we'll talk about why we wouldn't want to do it. So if you're on autopilot, you might think that you'd go -2, -1, 0, 1, 2. Not going to work. Okay, so let's talk about the negatives. Why won't the negatives work? When I try and plug a negative and ask what power that is of our base e, how are you going to raise a positive number to some power that's going to give you a negative? So the negatives are for sure canceled. Same thing for 0. How are you going to raise e to a power and produce you with the number 0? Because you're always multiplying 2.7 roughly by itself, so that just doesn't make sense. Okay, so then when we plug in 1 and 2, that would be acceptable. However, in terms of actually getting something like an exact coordinate, ln 2 is going to be not an easy number to, say, compute by hand. So if you did not have the benefit of graphing technology, I probably wouldn't choose 1 and 2 either. 1 would be okay, but I definitely wouldn't choose 1 and 2. So here's what I would choose instead for this one. So we're for sure staying away from the negatives, and we're going to try and think powers of e. When I plug in things for x, I want to plug in powers of the base, e. So I'm going to plug in e to the -2, e to the -1, and e to the 0, e to the 1, e to the 2. Okay, so that might feel like really weird values to plug in, but think about what you'd be getting for your y's if you were going to do that. So let's take a look at it. If I plug in e to the -2, I'll get ln of e to the -2, ln of e to the -1, ln of e to the 0, ln of e, ln of e squared. And let's simplify that. So ln asks the question, what power? So it wants to know what power of e is what's inside. Well, that's easy. It's staring right at you. -2. And what power of what's inside is this? Well, it's e literally raised to the power of -1. What power? 0. What power? 1. What power? 2. So because I made those choices for my x values to plug in, I have at least nice y values. With e, you're not going to get nice x values and nice y values. Something's going to be kind of gross. So if you don't like choosing these values of x and you just want to stick to like the basic 1 and like 1, 2, then you'll have, well, 1 isn't already a repeat value. We already hit 1 right here. So that's the same. You'd get 0. But if you try and plug in 2, you're going to get a very long decimal when you go to your calculator. And it's actually kind of cool how your calculator approximates it. But again, it's not the nicest. So as long as you guys make sure to not plug in negative values or 0, I'm happy with what you choose either way. But I guess I have a slight recommendation to focus on powers of the base for the easiest thing to graph. Okay, so enough jibber jabbering. Let's get into graphing this. So we already approximated the decimals for e to the -2. This would be 0.14, 0.37. These values look very familiar, right? 1, 2.72, and e squared would be 7.39. Okay, so let's graph it. So let's make sure I give myself enough space. Okay, so at 0.14, we're at -2. And at 0.37, we're at -1. And at 1, we're at 0. And at 2.72, we're at 1. And at 7.39, we're at 2. So the growth definitely slows down. Okay, so let's connect those. Looks like it swishes down here. Okay, and then we want to think about what's going to happen as we keep plugging in bigger and bigger powers of e. The powers will get bigger eventually. So that is going to slowly creep towards positive infinity. Okay, what happens as we go towards 0? Well, we already know you can't plug in 0. Okay, because you'll never, it's not a defined value, as you can't raise the positive base e to some power to produce a 0 number. Similarly, you can't do it and produce a negative number. So I shouldn't see anything plotted to the left of 0 because it's not defined for a logarithm. So what's going to happen as you get closer and closer to 0, it's because you're plugging in really, really large negative numbers as an exponent. So this is going to approach its asymptote at x equals 0. And the same story applies for these logarithms, which is that these can be transformed with our transformations, and the asymptote can shift as you do the transformations. So that's what our parent function, ln x, looks like. And the shape of a logarithm is going to stay the same across those transformations. Okay, so moving on. In general, what we just noticed, if we look between our two graphs, let me shrink this down. If we look between these two graphs here, you'll see that you have the points, x and y, they switched. So notice how the t-chart completely switched. Here and here. They switched between here and here. Isn't that pretty cool? Okay, the reason why that happens is because those two graphs are inverses of each other. So as you just learned, inverses are functions that undo each other. Logs undo exponentials and vice versa. In general, as long as you keep your base the same, So you need to have the same b. Then your log base b of x and your y equals b to the x are inverses of each other. Okay. So let's take a look at what this means. If I take log base b of b to the x, we've noticed that the log base b and the b to the x, they undo each other. So you would just get x outputted. And on the other side of that, if I tried to do b to the log base b of x, those will undo each other and you'll be left with x. So in general, there's always a relationship that can allow us to go from exponential form, which is, let's say b to the x equals y. Exponential form can be converted into logarithm form. Let's use another color. Log base b of y equals x. Okay, so these are equivalent expressions to each other, and sometimes it's more helpful to think of them, think of the other form basically. Okay, so let's take a look at how this might be helpful. When we're trying to simplify easy logarithms, technology is not always necessary, and I feel like sometimes the habit is that the calculator is safe, the calculator is comfortable, but keeping in mind that one thing that we are as early mathematicians, and many of you are going to be in the STEM field and not necessarily in mathematics, you guys might find yourself being the people that have to program. And if you do find yourself being someone who has to program, you would need to know exactly what the calculator or whatever you're programming is doing. So it's definitely an important idea to not lose the meaning of what your calculator is computing. We should be able to at least check this kind of stuff. So we're going to simplify this without technology. And then I will show you guys how we can use calculators to evaluate these expressions as well. So looking at something like log base 2 of 4. Starting on example A here. Okay, so notice, what is the base? The base is the subscript. So the base is 2. And we're asking the question, what power is the argument? What power of 2 is 4? So this is logarithmic form. Let's write it in exponential form. If we say that, if we call the answer to the problem x, then this is saying that 2 to the x equals 4. And when I rewrite this expression in exponential form, I find that most students are way fast at answering what the x value is. So the x value here would clearly be 2. And I'm just going to write 2 because that is what log base 2 of 4 is equal to. And there's our answer. So log base 2 of 4 equals 2. If you guys want to be precise and just really careful in explaining what you mean, you can write that part. But if you just wrote 2, that would be fine as well. Okay, so let's try that with the next one. Okay, so rewriting it in exponential form, 2 to the x equals 1/4. And it might help us when we have these fractions to write what we do know is a power of 2. Do you guys agree that 4 is 2 squared? So when you see it in the denominator, that means that your x should be a negative. So that would be negative 2. And let's take a look at the next one. If we're looking at ln of e to the 5th, this is asking the question, what power of e is e to the 5th? And hopefully it really looks similar here because it would just be 5, right? Okay, and this one, ooh, D, I've got tricks. I've got tricks up my sleeve with part D. So we've got a lot of stuff going on, and the biggest mistake I'll see students is try and work outside in, and you have to work from the inside out. So I see a composition of functions here, and the innermost function is the ln 5. Okay, so there's our innermost function, and I can't compute what that is exactly, so don't even try, because I know that 5 is not an easy power of e. But I see that it is the power on e here. So e to the ln, that's going to undo itself. So I'll be left with e to the ln of 5 would just be 5. So I'll be left with ln 5. And that's as simple as we can get this without using technology. So if we got our calculator involved, it would just give us a decimal. It wouldn't give us the exact value. So that's unfortunate for computations. Like if I needed to use this as something continuing on in a problem, I wouldn't want to switch to decimals at this point. I'd actually want to keep it ln 5 because that keeps your margin of error lower. Okay, let's move on. Do another base here. Log base 4 of 64. If I write equal to x, that would be 4 to the x equals 64. So that would be power of 3. And 4 to the x equals 1 over 64 would be negative 3. There we go. So now that we've practiced simplifying some basics here, let's take a look at how we can do this on our TI-84. And I'm going to demonstrate with a TI-84CE. If you have a TI-83, it's going to depend on your specific, like how old is your TI-83, how up to date is it. But there is a workaround for TI-83s, and it won't be covered in this video, but it is something that's pretty easy to find online. What I'll say to help you guys out that are using a TI-83 is you will want to use the change of base formula. And that's going to be something that we get to in another video coming up. So let's move on to the TI-84CE. So let's move on to inputting some logarithms in different pages into the calculator. So the most common one we're going to be working with is our log base e, and there is conveniently a key that's already preloaded on the calculator. So if I want an approximate decimal for a value of ln, I could put in ln of 4, and there's our decimal. Let's take a look at what it does when we know the exact value for something. So if I put in ln of e to the power of 2, we know from our work earlier that we're expecting the calculator to say 2. Let's see how it handles it. Perfect. So it got the exact correct answer. Okay, so that's log base e. Let's say we want to do something in log base 10. So let's put in log base 10. So you'll notice the calculator does not have a base 10 typed because it's typical, just like with logarithms, that people will drop off the base 10 in the notation. So you'll just hit the log key. And if I put in 100, I should be getting 2 because that's 10 squared. And yes, we got 2 again. Okay, so that's base e and base 10. Let's say I want to take the logarithm of some other base. If you hit the math key and you scroll on down to option A, on the TI-84CE, it has it nicely formatted and you can put in what you want your base to be. So if I want to compute log base 2 of, let's say, 4, I'm expecting to get 2 back as an answer, and there we go. That's how we do pretty much any base on the TI-84CE.